This is homework help for related rates. This is number 17 from section 3.10. So here we have a man of height 1.8 meters. Okay, so we're going to have a guy that's walking, and he is 1.8 meters tall. And he is walking away from a 5-meter lamppost. Okay, so this right here is 5 meters, and it's a lamppost, and there is someone walking away from it, and this person right here is 1.8 meters. And so what we have is we have a triangle right here. Okay, so the man is 1.8 meters tall, and he is walking away from the lamppost at a speed of 1.2 meters per second. So this direction right here is 1.2 meters per second. Find the rate at which his shadow is increasing in length. So what we are looking for right here is we are looking for this right here. It's when it's increasing. We are looking for the rate that this person's shadow is increasing as he is walking away from the lamppost. So this is the lamppost right here. This is the lamppost right here. Okay, now likely when you saw this problem, likely what you tried to do was use the Pythagorean theorem. But that is not what we're going to do. We're going to go back to geometry, and we are going to think about similar triangles. Similar triangles. So this is a right angle right here, and this is also a right angle right here. So what we have is a triangle, a large triangle, and then we have a smaller triangle. Okay, so what we're looking at right here is we can talk about proportion. We can talk about proportions. So this distance and this distance right here. Okay, so this part of our triangle and this part of our triangle is going to have the same relationship as this part of this smaller triangle and this triangle right here. So let's label a few things. So we're going to label this as x. This distance right here is going to be x. And this distance right here is going to be y. We're going to label this one y. So what we're looking for is the rate of change of this distance y. That's what we're looking for, the rate of change right here. Okay, now the rate of change for x and y together is 1.2 meters per second. I'm sorry, just the rate of change for x is 1.2 meters per second. This right here. Now remember, related rates are always dealing with time. So we have to think about how does this relate back to time. And this is where the trick is for this one, the one that might cause you a little bit of you have to think a little bit harder here. And that's this distance right here can be represented by time. So this is our man right here. He's walking away from our lamppost. So to figure out this distance right here, we can say it is 1.2 meters times the amount of time that he travels. So if he's traveled 1 second, he's traveled 1.2 meters. If he's traveled 2 seconds, it's 2.4 meters. 3 seconds is 3.6 meters. So this distance x right here is going to be 1.2 times the time. And that's the part right here. This distance right here is probably where we get stuck. Once we figure that out and how to show that distance, then we're able to solve these similar triangles. So if you remember back from geometry, the relationship here to this relationship here is proportional to the relationship here to the relationship here. Okay, they've got two angles that are the same. And if you've got two angles that are the same, then all three of them are the same. So here's a right angle, here's a right angle, and this angle is shared by both triangles. Okay, so now what we do is we set up a proportion. We haven't done any of the calculus yet. Everything here that we've looked at is just algebra and geometry. So to illustrate this total distance of the bigger triangle, so let me draw a bigger triangle. Here's my bigger triangle right here. Okay, and we know this is 5. This is going to be 1.2t plus y. Okay, so this distance right here is the distance the man has walked away, and that's 1.2 times t. Okay, then we're going to have our smaller triangle. Okay, we know this is 1.8 because the man's 1.8 meters tall, and here's the distance y. Okay, so we can set up this proportion in a couple of different ways. Okay, you can, as long as you set it up proportionally, you're good. So what I'm going to do is I'm going to start with this side right here, and I'm going to say y over 1.8. Okay, so I have y over 1.8 equals this distance, which is 1.2t plus y over 5. It's just a proportion, and that's the definition of similar triangles. Okay, so I've got 1.2t plus y over 5. Okay, and again, I haven't done any calculus. Okay, so remember, related rates are always going to be in terms of our t. So all I'm going to do now is I'm going to solve for y. So I'm going to have y equals on one side, and I'm going to have something on the other side multiplied or divided for our t. So I'm going to do cross multiplication. And so I've got 5y equals 1.8 times 1.2t plus y. Okay, so then I multiply the 1.8. I'm going to distribute that. And I end up with 2.16t plus 1.8y. Okay. I get my y on the same side, so I've got 3.2y equals 2.16t. I'm solving for y. So then I divide both sides by 3.2, and I get y equals 0.675t. Okay, now again, all of that's just geometry and algebra. Okay, now I want to know the rate at which this distance y is changing. So that's why I solve for y, and I've got it in terms of t. So now I just take the derivative. So dy dt is just going to be 1 because I've got my y right there. So it's dy dt equals, and then I'm going to take the derivative because it's always in terms of y, or in reference to, I'm sorry, we're differentiating in the relationship of t. And so here we've got 0.675. Okay, so the rate of change for the distance y that we're talking about is 0.675 meters per second. Okay, so this one, you probably didn't think to set it up with similar triangles because we didn't really talk about that. So setting it up with similar triangles is the way to do it. You likely tried to set it up with x squared and y squared and the hypotenuse, and that's probably, thinking about similar triangles is really the trick here. And so this is our answer right here.